All right, let's take a look at some word problems. So a radioactive sample of radium has a half-life of 15 days. The mass m in grams of Ra-225 remaining over time t in 15-day intervals can be modeled using the exponential graph shown below. What is the initial mass in the sample? What value does the mass of remaining approach as time passes? So this information can be taken off of the graph. So what is the initial mass? Well, it looks like it starts right here, and that's 1, and we look at our units at 1 gram. Okay, so we have a mass of 1 gram. Now, what value does the mass approach? Well, this is an exponential decay. It approaches 0, and we're kind of going into calculus just a little bit here as we're talking about approaching. It never reaches 0, but it does approach it, so it approaches 0. Okay, next, B, what are the domain and range of this function? Okay, well, let's do our domain first. Well, our graph starts at 0 days. It is possible to have exactly 0 days. And then it looks like it could go on forever. So then we're going to have infinity there. And sorry, this doesn't start at 0 days. It's actually 0 15-day intervals as well. And then we have our range. Well, the largest value we can have, which was our initial mass, is 1. And the smallest is almost 0. Now, almost meaning it's not going to be a square bracket. It's going to approach 0. And then our largest will include 1 as our value. All right, finally C, write the exponential decay model that relates the mass. So we just did some questions like this. We're going to find as x increases by 1 what's happening. So I'm looking here from 1 to 2. I'm getting the values of 0.5 to 0.25. So we're going to find out 0.5 times something gets me 0.25. Well, let's do some division there to figure out what that is. And again, you might already know without doing the division that this is going to equal 0.5. I'm not going to put it as 1/2 because we were given decimals in the equation, a question, so that's why I'm going to leave it as a decimal. So that's my b value, and therefore we have this graph of y equals our b value of 0.5 to the power of x. All right, our final question for 7.1. Under ideal circumstances, a certain bacteria population triples every week. This is modeled by the following exponential graph. So what are the domain and range of this function? So looking at our bacteria, it looks like we start at 1 and it keeps on growing. So therefore our domain, so we can have, for our weeks, looks like we can have 0 weeks. So we're going to include that. And we don't know where this stops. This could go on forever, so that means it's going to go to infinity then. And then for our range, well, the smallest number of bacteria we have, it looks like is 1. And it can be exactly 1. And this grows forever, so it will also go to infinity. B, write the exponential growth model that relates the number b of bacteria to time t in weeks. So again, we're looking for what happens as x increases by 1. So from here to here, we've got an increase of 1 in the x. Let's look at those y values. It looks like they go from 3 to 9. So 3 times something is going to give me 9. Now 3 times 3. So therefore, b, our base is 3. And we can say, well, we got to be careful here because we've got this capital B. So it's not y equals, it's going to be b equals, our base is 3 to the power of t. And then C, determine approximately how many days it would take for the number of bacteria to increase to 8 times the quantity on day 1. Well, that means my B is equal to 8, and 3 is still my base, and we're looking for what T is. Now, we could estimate, we could use a calculator and punch values into T until we finally get really close or make like a table of values. But at this point, the easiest and most accurate is actually going to be to use a graph. And so I already have these graphed out here. This blue line is our y equals 3 to the power of x. And then this red line is our left side, or y equals 8. and we can see it's approximately 1.9. So we go back. That means that t is approximately 1.9, and that's in weeks.